Hello students, our today's reaction is Friedel craft alkylation. So reaction is Friedel crafts alkylation. See what happens here in this reaction, the benzene is converted to alkyl benzene by treating it with suitable alkyl halide in presence of some Lewis acid. Here, this Lewis acid, this one acts as a catalyst, like anhydrous AlCl3, BF3, FeCl3, etc. are the examples of the Lewis acid. We may write the reaction in this manner. See, there is a benzene ring, and when this benzene is treated with alkyl halide, I am taking here alkyl chloride, in presence of anhydrous AlCl3, like warming is required. See, carbon halogen bond breaking occurs, and as a result, one of the hydrogen of the ring is replaced by the alkyl group, and the hydrogen which sets free from the ring combines to the Cl minus and forms HCl. And here we obtain alkyl benzene. Is it clear? Now we'll discuss how the reaction occurs, means the mechanism of the reaction. See, this one, Friedel-Crafts alkylation reaction, is an example of the electrophilic substitution reaction. See, as you know, in a benzene ring, there is a cloud of 6 electrons above and below the plane of the ring, and that's why this benzene becomes susceptible for the electrophilic attack. And at the same time, this benzene remains stabilized by the presence of resonance, and that's why benzene usually undergoes electrophilic substitution reaction instead of addition. See how the reaction occurs. Here, let our alkyl halide is methyl chloride. Now, our methyl chloride will react with the catalyst. The catalyst taken here is anhydrous AlCl3. In this anhydrous AlCl3, the central Al atom is having 6 valency electron. Means this one is electron deficient. There's a deficiency of the 2 electrons. So in order to compensate the deficiency of this Al, this carbon-chlorine bond breaking occurs, and the Cl comes out along with the electron pair of CCl bond in the form of chloride ion, and combines with anhydrous AlCl3 and forms AlCl4 minus or AlCl3.Cl minus. See, this carbon has lost the electron. Now we'll get a electron deficient species, and this one carbonium ion is obtained, and which will act as a electrophile. See, this one is our first step. So Friedel-Crafts alkylation accompanied or takes place in the 3 steps. So in step 1, this involves generation of electrophile. So in the first step, electrophile is generated. Now in step 2, this electrophile which is generated here in the first step, this attacks over the ring. As you know that in benzene ring there is a cloud of electron. It's an electron cloud. And now the electrophile approaches the ring. Now making the use of, out of these 6 electron cloud, making use of 2 electrons, this ring forms bond with the electrophile. And as we know, at each position of the ring, there's one hydrogen. Now in the cloud there will be 4 electrons will left. Means the ring will become electron deficient and means the slight positive charge. So this one is the step 2nd. Now in order to write the, explain the mechanism over paper, we make use here resonating structure of benzene as proposed by the Kekulé. So here this is one of the resonating structure for benzene. Now the electrophile CS3 approaches the ring. What happens? Making use of these 2 electrons, ring will form bond with the CS3. See here, these 2 double bonds will remain unaffected, while here, as these 2 electrons are used up in forming the bond with the electrophile, see, in this bond, one electron comes from this carbon, other one from this. As the CS3 has formed bond with this carbon, so another carbon will become electron deficient. In order to and here there is the CS3. This type of carboniamine or carbocation is formed. The carbocation thus obtained remains stabilized by the presence of the resonance. In order to compensate the positive charge of this carbon, the pitons of adjacent bond shifted here. We'll get the another resonating structure. Now double bond will here. As these 2 electrons shifted this place, double bond will form here. This carbon will become now electropositive. And at the ring, there is one H and CS3. Now again, in order to compensate its positive charge, this adjacent piton will shift here. One more resonating structure is formed here, double bond. As these 2 electrons shifted here, so here double bond will form. This carbon will become electron deficient. Here there is a H and CS3. Actual structure is none of these. These are the possible resonating structures. Actual structure is none of these. Actual structure lies in between of all these possible structures. Here, the positive charge is rotating over the ring, and at the ring there is hydrogen and CS3. This one is known as resonance hybrid. Is it clear? Now, the third step. In the third step, this resonance hybrid, or you may call it, is a sigma complex. This resonance hybrid sets free this hydrogen, which has to be replaced as a proton. Now, what happens here? In step 3, the the carbocation loses a proton, and here this carbocation or resonance hybrid reacts with AlCl3.Cl minus or AlCl4 minus, and now this AlCl4 removes the hydrogen as proton. Now the H plus sets free from here, combines to the Cl minus, comes out as HCl, and this AlCl3 anhydrous will set free, and now the deficiency of the ring will be compensated, and finally we will get our alkyl benzene. As here the alkyl group is methyl, so our end product will be methyl benzene. Is it clear? See what happens here. See, as the 2 electrons of the cloud gets consumed in forming the bond with the CS3 plus, means electrophile, and now ring itself got the electron deficient, and now to compensate the deficiency of the ring, the hydrogen which has to be replaced, this CH bond electron will be donated to the ring, and finally the cloud of 6 electrons of the ring will be compensated, and the H plus will set free. Now this H plus will combine to the AlCl3.Cl minus and will set free with the Cl minus in the form of HCl. Is it clear? So this is the mechanism of the reaction.